These are the frequently asked questions for pre-calculus for section A2. I'm going to start with number 27. And for number 27, it occurs to me that maybe the problem was the use of U and V for the formula for this one. And what you need to know is the letters don't matter. So let me give you the formula using A and B. What we have to do is take the first term and start it at its highest power and then work our way down. And we go all the way down to a to the 0. And then we take the second term, which is b, and we start that at b to the 0, which is 1, so I'm not even going to write it down. B to the first, b to the second, b to the third. And then we remember from Pascal's triangle that the third row is 1, 3, 3, 1. And finally, since this has subtraction, we need to oscillate positive, negative, positive, negative. So like I said, if it is truly the letters, don't let that bother you. Use whatever letters you want to. My first term, my A term, is 2u, and my second term is v. So now I just need to substitute those in and see what I get. So a cubed will be 2u cubed minus 3 times 2u squared times v. All I'm doing is substituting 2u in for a and v in for b, plus 3 times 2u times v squared minus v to the third. And now we're going to simplify. 2 to the third is 8, so 8u cubed. Follow the order of operations for the second term. 2 squared is 4, 4 times 3 is 12. Then we have 3 times 2 is 6, uv squared minus v to the third. And you have it done. So again, don't let the letters mess with you here. All right, the next one was number 33. And 33, in the directions up here, they had said to use vertical alignment. So what we want to do for 33 is write x squared plus x minus 3. And we're going to take that times x squared plus x plus 1. So that's our vertical alignment. And then just do this as you did back in grade school. So we're going to take a 1 times everything up above. So that will give us x squared plus x minus 3. Then we take x times everything up above, and that will give us x to the third plus x squared minus 3x. Then we take an x squared times everything up above, and that will give us x to the fourth plus x to the third minus 3x squared. And that didn't line up very good there, so hang on a second. Let me get this lined up a little better. There we go. All right, and now we can go ahead and add these vertically. Negative 3, x minus 3x is negative 2x. X squared plus x squared is 2x squared minus 3x squared will be a negative x squared. X to the third plus x to the third is 2x to the third. And then we have that with our x to the fourth out in front. So there's our product, and again, that is done vertically there so that we can see exactly where everything is coming from. Now that wouldn't be the only way to do it, but it's a good way to do it to keep organized. Then for number 36, this one did not have any directions besides expanding that product. So when you look at 36, what you need to remember is these are binomials here. And we really have x to the 1/2 minus y to the 1/2 times x to the 1/2 plus y to the 1/2. And that means this is that sum and difference pattern. So what that tells us is from FOIL, we don't have to do O and I. The positive and the negative will make those cancel out. We need first times first. Well, x to the 1/2 times x to the 1/2, and last times last, the negative y to the 1/2 times y to the 1/2. Well, when you multiply similar bases, you add the exponents. So 1/2 plus 1/2 will give us 1x, and 1/2 plus 1/2 will give us 1y. Now, what we don't want to lose track of is the fact that these were really radicals. This was x to the 1/2, which means it was the square root of x. And this was y to the 1/2, which means it was the square root of y. And whenever we're dealing with square roots, then our values have to be positive. So we should tell them, you know, this is the domain. We realize that because there are square roots, x will have to be greater than or equal to 0, and y will have to be greater than or equal to 0. Then you had asked about number 56, and this was factoring the sum or difference of two cubes. So the first thing you look at in 56 is whether or not we do have a common monomial factor. And, you know, at 27 in the back, you're thinking, hey, maybe I could pull a 3 out, a 9 out, you know, what can I do? And we can't. But that's okay, because this is a perfect cube, and this is a perfect cube. And again, you don't have to use u's and v's if you don't want to, but what you do have to do is remember the formulas. And this one would be a plus b times a squared minus ab, to get rid of any middle term, plus b squared. So this is the formula for a cubed plus b cubed. Well, that means my a value up here is 4z, and my b value is 3, because that is what you would cube to get those perfect cubes. So that will give me 4z plus 3 times, well, if you take 4z and you square it, you get 16z squared, minus a times b, which is 12z, plus b, which is 3 squared, is 9. And we have followed the pattern there that we need to follow whenever we want to factor the sum of two cubes. This last group, I was talking to you in class about how sometimes they're mixing things up a little bit just to try to, well, basically mess with your head. That's what they're doing. So 76 says factor completely. And I notice I can't pull a 4 out of everything because it won't come out of the 25. But I can definitely pull a y out of all of those terms. And that will give me 4y squared minus 20y plus 25. Now as I'm writing that down, I'm thinking, wait a minute, this is a perfect square. This is 2y squared. This is a perfect square. It's 5 squared. I wonder, if I multiply those two together and take the answer times 2, will I get the middle term? Well, 2y times 5 is 10y. 10y times 2 is 20y. So that means this can be written as one binomial squared. And I've already figured out what I need for the first and last terms. It's just a matter of noticing that this has subtraction in it. So that will be y times the quantity 2y minus 5 squared. So again, really important to know those patterns so that we can see those as we go through to factor. Number 77, similar situation. I see here that everything has a y, and then I start thinking, okay, is there any number that I could pull out of all of those? Well, they're all even, so at the very least a 2 is going to come out. And if I can't see something else, I'll probably just start with the 2y and see if something else becomes obvious. So with a 2y, I would need 9y squared plus 24y plus 16. Now, as I'm writing that down, I'm thinking, well, maybe this is another perfect square trinomial. Maybe, because this is 3y squared and this is 4 squared, let me check on that middle term. Well, 3y times 4 is 12y. And if I take that times 2, I do get that middle term. So this is a binomial squared. This would be the first term. This would be the last term. And because this is addition for the middle term, that would be a plus. So 2y times 3y plus 4, the quantity squared. Then, the next one on your list is 84. and we have 5 times the quantity 2x minus 3 squared minus 20. Well, first of all, you should be thinking, that is really strange. Why did they do that? Because they're hoping that you're going to see that you can take a 5 out of all of this. Because 5 times 4 is 20. Right, we take a 5 out of both of these terms, and we notice this is something squared, and this is something squared. This is 2 squared, and this is 2x minus 3 squared. So this is a little strange, but it is a difference of 2 squares pattern. So what we need is to know that the first term and the last term are going to be exactly the same, but because there's subtraction, we know that there's no middle term as we look in there, and that means all we had was first times first and last times last. So this had to be that difference of 2 squares pattern, which would be 2x minus 3 plus 2 and 2x minus 3 minus 2. Again, it's hard to think of 2x minus 3 as being the front term, but that's what it is. And then we can go ahead and simplify what's in the brackets, and this will be 2x minus 1 because we have a negative 3 plus 2, and then we have 2x minus 3 minus 2, which will be 2x minus 5. So, like I said, kind of strange. Now, how else could you get there? Well, you could multiply 2x minus 3 times 2x minus 3, get an answer, distribute the 5, then subtract the 20, and get this down to a trinomial that you would be able to factor. So that is another way to do it if that difference of 2 squares pattern is just not showing itself to you right there. All right, the next ones that you had issues with were the ones with grouping. And like we talked about in class, it's because they're making you move the terms around, which is something you generally haven't had to do before. In Algebra 2, we taught you how to factor by grouping, but you definitely didn't have to do any moving of terms. So 87. We start by grouping, and we say, all right, let's see, if I was going to group with these first two, I would have a 2, and that's it. Nothing else is going to factor out of that. And then in the back, well, I can't take a 4, I can't take an A, I can't take a D, and you realize, whoa, I can't factor this if I'm going to use this with grouping, unless we move the terms. What we have to do is try to figure out how we can get these terms together so that something would be pulled out of them. So I'm looking at this and thinking, all right, well, these two have an A in common, so maybe I'll try those two first. And then my 2 leftovers will have a B in common, so maybe that'll work out. So if I take a 2 and an A out of the front here, I will get C plus 2D. And in the back, if I pull out a negative B, I will get 2D plus C. Now, if you look at the parentheses, you realize it is the same thing. It's just backwards. And remember, the commutative property tells us that addition can be switched around. So now it looks like what we want. And now we can see that C plus 2D is a factor, and that 2A minus B was the other factor. And so we have that one in factored form. Number 90, similar. So I try just straight grouping right away, and I say, oh, I can pull an x third out of that, x to the third out of that. That'll leave me with x minus 4. In the back, well, I don't like that negative there, so I'm going to take a negative out of that, and I'm going to take an x. All right, if I do that, then this will need to be an x, and then this will be a minus 4. Hey, this time it's going to work. I don't have to move anything. So I see that I have all of this. Now, as I do that, I notice, wait a minute, there's x's in both of those positions. Well, that's because remember that your first step should always be factoring out that common monomial. And that is the piece that you forgot. At least in most cases, that's the piece that people are going to forget. So we have this x out in front because it's a common monomial factor, and then we still have to factor by grouping. So we group these two together, still have that x coming along, and that would be x squared times x minus 4. And then in the back, like I said, we could pull out a -1, and that will give us the x minus 4 that we need. So we have this x, we have x minus 4, and then we have x squared minus 1. And you think you're done, but remember, if we have anything that has a squared power or higher, it's possible it might still be factorable. And this is factorable because it's a difference of 2 squares. So we have x, x minus 4, x plus 1, and x minus 1. And that is now factored completely. That's a really nice factoring problem there. And make sure that we have to get to a lot of patterns that we've seen. And that should do it for this one.